have a coin C, mass of 0.005 kilograms placed on a horizontal disc at a distance of 0.14 meters from the center, as shown above. The disc rotates at a constant counterclockwise direction, as seen from above. The coin does not slip, and the time it takes the coin to make one complete revolution is 1.5 seconds. Now there's two ways to solve for the first. Oh, label all the vectors. Oh, okay. So first thing, we're going to label our velocity and we're going to label our acceleration. Okay? So we have a rotating object. It's rotating in a perfect circle. What can we say about its acceleration? Center pointing, centripetal.
Oh, yeah.
Okay? Cool. What about its linear velocity? It's tangential to the circle. Okay? Yeah, you're absolutely right. Because the circle is going in this direction, my linear velocity is in that direction. So here's my acceleration, here's my velocity. Okay? Got it? Does that make sense? Everybody on board? All right. To determine the linear speed of the coin, I'm going to ask you, how did you guys solve it? There's two ways to solve this, by the way. The circumference? Oh, get the circular speed. That's the second way to do it. Yep. If I know the rotational velocity, right? It does one revolution in 1.5 seconds. So it does 2 pi radians in 1.5 seconds. Okay, that's equal to my rotational velocity. And I can say my rotational velocity is equal to v over r. So I can then say 2 pi r over 1.56 is equal to my velocity. Right? Using the idea of rotational velocity is directly related to linear velocity as omega is to v over r. Okay? The other step, which most of you I think did, was circumference divided by speed, or time, gives me velocity. It's the same thing. Okay? And one thing you guys got to realize is that I shouldn't say velocity, I should say speed. Why should it be speed and not velocity? It's constantly changing direction. Cool? Got it? Everybody okay? No?
No, I'm not okay.
Oh, I'm sorry. Can I give you guys a hug or something? Alright, so the rate of rotation of the disc gradually increases. The coefficient of static friction between the coin and the disc is 0.5. Okay? Determine the linear speed of the coin in which it begins to slip. Anybody have any ideas? Is this where everybody's brain went kaplawi?
Yes, sir.
Yes, sir. Does it have an acceleration? Does the coin accelerate at all? Yes. What's the equation for its acceleration? I mean, I give you AC. What's the equation for its centripetal acceleration? V squared over R. Okay? If I wanted to turn this acceleration, well, hold up. And then we have Newton's second law, sum of my forces is equal to mass times acceleration. Right? What force is acting on this body? Friction. What's the equation for friction? U times normal. And in this case, what's my normal equal to in this case? The weight. Okay? It's exerting a force on the disc is exerting a force back equal to the amount that it's exerting. That's equal to its weight. So I end up with mu mg equals ma, right? Going over to the other side, I have mu g is equal to a. If I glue another coin to the top of that coin, will it make a difference? No. Masses cancel out. Most one-body problems, it does not affect the system. You increase the amount of weight the object has, but you increase the amount of force, meaning that it needs more force to move it. The amount of mass you increase it by is equivalent to the amount of force you have to increase it by. So it doesn't make a difference. Okay? The masses cancel out. It's irrelevant. Okay? And then at this point we've got mu g is equal to my acceleration, which is v squared over r. Solve for v. U is 0.5, g is 10, so you're looking at 0.5 times 5 times the radius, which is 0.14. Okay? Then take the square root of that and you have your maximum velocity. Cool? Got it? And then I've already answered D. In the experiment in part C, repeat it with the second identical coin glued to the top of the first one. How does that affect your answer in part C? It has no effect on my answer. I can glue 1,000 coins to the top of that one coin and it's not going to make a difference. Okay? The amount of force that's required to accelerate it is proportional to its amount of mass. Well, that force and mass are related. They're directly related. Yeah? Which part? The amount of force and the amount of mass thing? No, I don't think I ever mentioned that in a portfolio. For single body problems, the mass usually is not relevant. Or were you supposed to learn that? This is using Newton's second law and using universal circular motion in one equation. I know A is a result of a force. Okay? That's why we're doing it, so you guys can see that. Got it? Done? Everyone's got a solution? Yeah. All right.